Good morning or good afternoon. Very warm welcome to August 2023 ABC UTC monthly webinar. My name is El-Tawil, Azizin Amini, Director of the ABC UTC. A very warm welcome from Miami, Florida. Just a couple of, again, quick news. As we have mentioned in the last couple of webinars, we were glad to receive with the from the US DOT for the period of 2023 to 2029, a US DOT Tier 1 University Transportation Center. And our members, you see on this slides, Florida A&M, Texas A&M, and University of Georgia, University of Nevada, Reno, University of Oklahoma, University of Washington, our partner university. This time around, we are going beyond the ABC. We will be looking at the next generation of the ABC, given all this new technology. But also, in addition to that, we are going to be working in the area of trying to bring the innovative technologies, new ones that we are going to develop, or the ones that are used in the other industry, customize it for the bridge application. So there are some exciting time ahead. So our name is going to be IBT/ABC-UTC. Also, we are making a slight change to our operations, starting in the October monthly webinars. We are delighted to welcome Kathy Kroll, who is formerly was with New Mexico Department of Transportation, and she will be basically handling the monthly webinars, and that is going to allow the Mary Lou Rawls to concentrate on ABC project database. And Mary Lou is going to provide help when we need, but she will be concentrating on the ABC project database that is very popular with the bridge owners, and we are going to be enhancing it. So Mary Lou is going to be looking at the enhancing the project database using artificial intelligence and so on. We are also delighted to have with us now Dr. Bijan Khaledi, who was formerly with the Washington State DOT. And the Bijan is going to be in charge of technology implementation. That is very, very important to the US DOT and everything else that we are trying to do.
Our presentation today features the first bridge in the U.S. with 100% ultra-high performance concrete superstructure, Michigan's Bricker Road Bridge over Quackenbush Drain in St. Clair County. We're pleased to welcome our presenters, Bill Hazelton, Managing Director of the St. Clair County Road Commission in Michigan, and Sherif El-Tawil, the Antoine E. Naaman Collegiate Professor of Civil and Environmental Engineering at the University of Michigan and co-founder of Hyper Fiber LLC. We're pleased to also introduce additional members of the Q&A panel, Dwayne Rogers, Managing Director of Michigan's Clair County Road Commission, and Ben Graybill, Team Leader for Bridge Engineering Research at the Federal Highway Administration's Turner Fairbank Highway Research Center. In addition, we'd like to introduce our Q&A session moderators, Rick Liptak, Chief Bridge Construction Engineer with the Michigan Department of Transportation, and Paul Lyles, former Georgia State Bridge Engineer, both members of our ABC UTC Advisory Committee. We'll now begin the featured presentation. Bill?
Thanks, Mary Lou. So this presentation is about a bridge that we worked on last year with Sherif. Over the years, we've been thinking about UHPC, using it in small doses of different projects, and we felt, why not try this on a superstructure replacement project? So in St. Clair County, we have a lot of bridges. I say a lot, probably 235 or so. So this one was easy to find. We found some projects, and we started here. So the history behind it with us is we started this in 2017 using UHPC as for maintenance only. So we have a large problem with precast units from the 80s, and the connections of them seem to fail, and then the bridge fails. And then we have bridges from the 80s that we have to replace, which isn't good for us. So look for a more robust connection media, and that's where we started working with Sherif and his team and the UHPC mixture he developed. So since 2017, we've worked on about 11 bridges. 10 of them were only for joint replacements and things like that. And then this is the 11th one where we started doing a whole superstructure. This project was funded in part by the NCHRP grant through Sherif's assistance. So the old bridge wasn't very large. It was dual 120 inch by 80 inch steel arch pipes. The route was 3 miles for the detour. Flow wasn't crazy. It was only 290 CFS. But again, we have to meet requirements of our local Eagle. That's our EPA division here in Michigan. ADT was 300 vehicles per day. We have our own structural designer in-house, but we did get some consulting help from TEG. One of the problems we have, I guess, ultimately is the span of this thing, because we have to find a way to put guardrail posts to it. So we capped the length at about 24 feet, so we could just do a long span guardrail here in Michigan, and the posts are off the bridge. So, and with this project, we prefer to do ABC jobs now anyway. So this worked out good with the panels. We also use the precast ready rock blocks with a strip footing. Again, ABC. Approaches were concrete. We had to wait for those to cure. It wasn't ABC. Ultimately, the construction took about 4 weeks. We had a holiday in there too, so we had a week or so off to let the concrete cure, so that worked around the holidays. So in the end, we finished off the bridge with the epoxy overlay over the whole thing. So here's what the location of the bridge is. It's in Michigan here, just north of Detroit, probably about half hour. It's a gravel road located near the border to Canada. It's a local gravel road. It doesn't have high traffic, but it is important to the local area for farming and just moving goods back and forth. So this is a picture of the finished bridge. You can see the ready rock blocks. They have a nice aesthetic view to them. And then below the guardrail there, those are our precast panels that we developed with Sherif and TEG and installed. In the end, it worked out pretty nice, and aesthetically, it's got a nice look to it that our guys are very proud of when we built it. So also with this, we were able to secure an award for short span bridges recently. And in the end, it turned out really well, and I think that deserved the award in the end. So.
All right, Bill, I will take over from here. Thank you. Before I go further, I would like to remind you of the very first slide that I'm wearing 2 hats. I'm wearing the hat as a professor and also as a co-founder of a company that manufactures steel fibers. So I just wanted to be clear that I'm wearing those 2 hats, because what I'm presenting, I cannot separate them out into 2 distinct efforts. They are very much interrelated. So picking up from where Bill ended, and because I don't know the background of the attendees, I just want to describe a little bit what UHPC is. So it's a class of cementitious materials. I think of it as a next generation concrete that has a suite of enhanced properties. These are typically fresh properties like flowability, mechanical properties like strength and toughness, and durability properties. There's no agreed upon definition for UHPC, but there's general consensus that if you can achieve 150 megapascal, which is about 22 KSI, you have a UHPC. So this slide here kind of shows the difference between them if you were to slice a piece of concrete and UHPC. Notice that the one on the right is 5 times magnified over the one on the left, so you can see some of the features. So you're all familiar with concrete, but the UHPC, you notice the uniformity of the surface. And that is the key difference between them. There's really no big aggregate in the UHPC. So why is it such a unique why is it such a unique material with unique properties? Well, it's because of the high packing density. The sands in the material, there are 2 of them. They fit such that one of the small particles of the fine sand fit in between some of the larger sand particles. In between that fit in the cement particles. In between that fits in the silica fume particles. This what we call packing density is quite high, much higher than regular concrete. Another reason why it's so successful is because of this continuous pore structure. So if you look at the slice on the right, and you can see the 500 micron range at the bottom there, you'll notice that the pores are not connected. The discontinuity of the pores is one of the reasons why the material is so impermeable to water. And if you kill the water cycle, you basically kill the freeze-thaw cycle and you get this exceptional durability. And the third reason is the presence of steel fibers, because that influences the mechanical properties of the material. So the fibers are not an option in UHPC, you have to use them. And basically their purpose is to hold together the material. They kind of make it like if it tries to crack, the fibers say, no, we're gonna grab you together and hold you together. They promote something called strain hardening behavior, which I will explain in a second. But in order to get these benefits, you have to ensure optimal bond between the fiber and the surrounding matrix. If the bond is too high, the fiber will just break. And all you have done is just wasted the fiber. You've just increased the strength slightly, but no ductility. If the bond is too low, the fibers will pull out. And again, limited contribution. So it has to be just right. And if you get that correct, then that's when you have UHPC. So on the right there, I have an interesting statistic. A cubic yard with 2% by volumes fiber, that's how we measure it by volume, has 37 million individual fibers. If you put them end to end, that's 300 miles of wire chopped into half-inch pieces. So with so much effort, you must have really high expectations. And indeed, you should. So looking at the tensile response, which is one of the key properties of UHPC, you can see concrete at the bottom left, all the way down here. You can see that once it cracks, it loses all ability to support load and drops right away. But UHPC is different. Basically, the first crack forms. The fibers say, no, I'm not gonna allow you to fail, and they bridge it. And then another crack happens, and a third, and a fourth, and a 20th crack. And when this happens, basically, we call this behavior strain hardening, or the multiple cracking phase. The material does not fail upon first cracking. However, as you keep loading it, inexorably, one of the cracks, the fibers there, for some statistical reason, will not be able to support the load. They will start to slip out. And when that occurs, you basically go into the softening regime. So first is the elastic strain hardening, which is quite extended, as you can see, and then strain softening. The transition between the strain hardening and strain softening is called the localization strain. So please remember this word because I'll be using it quite a bit later on. You can see that the localization strain is about 2 orders of magnitude more than that of concrete. That is in the range to 50 to 100 times. The toughness is many orders of magnitude as well. And this is a picture from a test that you can see the localization strain. You can see the fibers that were trying to sew it together, but they couldn't and failed. You can see, if you look carefully, the very fine hairline cracks around that are fanning around this particular crack here. Okay, those are the types of cracks that I mentioned. And if you remember in undergrad school, when we took reinforced concrete design, we know that concrete is cracked. You have a number of large cracks under service conditions. We were always told that is okay, and that's certainly okay. But of course, they're large enough that we do have ingress of moisture and chloride ions, as you can tell from many of the bridges you drive under. However, UHPC, it does have bar reinforcement. Some people might think that it doesn't, but you do need bar reinforcement. But the difference is that because of its cracking process, you have a dense hairline set of cracks that are so fine that they inhibit moisture and chloride ions from reaching the reinforcement. And that is one of the big benefits of building with UHPC. In a way, I almost think of it like a pre-stressed concrete member, although of course it's not. And you can pre-stress UHPC members too. Now, something pretty momentous happened a couple of months ago, and that is the AASHTO Committee on Bridges and Structures approved the guide that was proposed by the Federal Highway Administration under the leadership of Ben Graybiel, who's one of the panelists. I think this is a really important thing that will broaden the use of UHPC in the US. And one other interesting thing is that this document imposed performance requirements on the tensile behavior of UHPC because that is so critical to response. Remember this localization strain that I mentioned a second ago? And this was approved unanimously. I was there at the meeting, and it was very interesting that that happened. A few questions here and there, but in the end, unanimous approval. All right. So with this long introduction to UHPC, I'd like to come to the project that we're here to talk about. And this was funded by NCHRP 2030 under the IDEA 235 project. The project title was High Bond Steel Fibers for Ultra High Performance Concrete. The award was to the company Hyperfiber, and the objectives were to investigate a new type of steel fiber that was being produced by the company, to assess its effect on the composite properties of the material, and to conduct a demonstration project. That's the Bricker Road Bridge project that I'm here to talk about. Now, the reason this was funded is because of the type of fibers that are available. So Hyperfiber makes these striated fibers. Basically, the fiber surface has striations in them. They are just microns deep and microns wide, and you can barely see them. In most cases, you cannot see them unless under certain light conditions. These fibers are compliant with the Buy America Act. They are made in the US and they're commercially available in the US. But I don't want to, this is not to talk about, Hyperfiber as a company or anything like that. I just want to talk about the bridge itself. But you had to know what went into it. So as Bill mentioned, this was a total bridge replacement project. It was 24 feet by 36 feet wide. It had new precast block abutments and wing walls. And what was unique about it was the triple T UHPC deck panels that I'm going to talk about. These were truck mixed using an open recipe, which I'm going to talk about in a second. So this is kind of a preview of the presentation. They were precast and cured at a local precaster, and they were assembled in the field by the county workforce. The Type X fibers that were used, they could be replaced by generic smooth steel fibers. You could do that, and you should keep that in mind as we go forward. There is a part towards the end where I talk about specific capabilities of this type of fiber, but for this particular project, you could have replaced them with generic steel fibers. Now, this is the mix that was developed for the Michigan Department of Transportation in 2014. It has been used now in numerous projects and is the basis of many mixes that developed around the country, the non-proprietary mixes. So you can see that it's made up of cement, slag cement, two types of sand. Remember where I mentioned one particle fits inside the others, silica fume, water, and a high range water reducer. And of course, the steel fibers. There are a range of mixes, it's a family of mixes, and the main difference between them is the amount of super plasticizer that you could use. So you first start with mix A and work yourself up until a mix that works in a batch situation. These are the sands that I mentioned. On the left is the large particle sand. You can see again how big 500 microns is. This sand typically would have a median size of about 600 to 800 microns. The finer sand on the right is about 150 to 200 microns. According to packing theory, this fits in between the larger sand particles, fits very neatly in there, okay? And from some of our earlier research on UHPC, this is the freeze-thaw test under the Rylam method. On the right, you can see the performance of two different types of concrete. On the left are different mixes made from UHPC, and you can see that the performance is 2 orders of magnitude less mass loss compared to regular concrete. And that's why we think this material has such terrific durability properties. We tested it up to 96 cycles until we got kind of tired of testing it. These are expensive tests to conduct. They take many days to do, but others have tested it up to several hundred cycles, and again, with exceptional performance. This is another test that we did as well, many years ago. This was the rapid chloride test, and it measures the charge that is passed in a slice of this material. And again, you can see the concrete on the right, 2 different formulations. And on the left, you can see again, 2 orders of magnitude less performance for some of the UHPC mixes that we investigated. So the mixing protocol is one of the, I think, things that a lot of people find to be difficult or think that this is not feasible to do, but it is very feasible. This is the mixing protocol that we used. We dry mix the material for 15 minutes. Typically, this is actually a function of the truck and where it's going and where it's coming from. And so in the lab, we typically mix for 5 to 7 minutes, but in the truck, we mix for longer. Then you add the water and high range water reducer, you mix them together and then add it in slowly. And then you wait for fluidity, we call it turnover, which happens about 5 minutes after the water is added. You wait another 5 minutes to make sure that it has turned over well, and then basically add the fibers. It says here 10 minutes, but that's really a practical limitation of adding the fibers because they come in bags. And so you kind of dump them in one after the other. It takes a while to do so. And then you mix for another 10 minutes and then you cast. This was done in a truck, in a ready mix truck. And at the time when we did this, we had never done this before. And so we were quite worried whether it would work or not. But thankfully, it has worked. It has worked numerous times since. And I'm going to come to this topic back again very shortly. This here is the consistency of well-mixed UHPC. I wanted you to see it so you can see that it's quite different from concrete. You can see that it falls in clumps And that's because of the unique viscosity of the material. It kind of drips in. And you know that it's well mixed when it has the consistency of milkshake, basically. Now, as part of this NCHRP project, we conducted testing. So these are compressive tests. You can see that they are made on cubes. The reason we conducted them on cubes was because the third-party testing company did not have the capability to break cylinders. And testing that Ben Graybiel had done had shown that actually the difference between the cubes and the cylinders was pretty small. And so in this particular case, the cubes had a capacity of close to 27.5 KSI. And a Young's modulus of about 8,700 KSI. Young's modulus is something a lot of people do not know about UHPC, that it's so high. It's about twice that for regular concrete. And that has pretty important implications for pre-stressed concrete design in terms of loss in the steel, and especially when you're initially stressing it, and also for high-rise building when you are worried about differential movement between the columns as you go, to the 50th and 100th stories of your building. So the Young's modulus is a very useful property of UHPC. Intention for this batch of tests, the localization strain, remember that is the delineation between strain hardening and strain softening, was 0.43%. And just so you can compare, steel yields at 0.2%, right? So you can see that the material will continue to remain in the strain hardening range, even well beyond steel yielding. So again, this is an important design parameter to keep in mind as we go forward. These tests are conducted by making a coupon and basically ripping it apart in the machine, as shown on the left. Now, when we came to the design, we were a little confused. Okay, should we use the parameters from the tests? Will we be able to get those in the field, even though we'd never mixed this in the field before? Would it mix well in a truck? There were a lot of unknowns, and this was a kind of a hair-raising moment, at least for me at the time. So we basically used assumed properties that were a little bit lower than the test parameters or what we got in the lab. And then we said we would check towards the end from the trucks, and I'm going to show this data shortly. So for example, the compressive strength that we got in the lab was 27 KSI. We assumed 21.5 KSI. Going all the way down, the localization strain was 0.43%, 0.0043. We assumed it to be 0.0025, which is the minimum allowed at the time by the Federal Highway guidelines. By the way, that was not yet approved, so we were kind of using it just for guidance. Also, the tensile strength of the material, which you cannot ignore because it's so high, it was 1.82 in the tests. It's 1.15, okay, for the design. And because, again, remember, when we did this, the guidelines had not yet been approved, and so we were kind of on our own. And so we reverted to first principles to conduct the flexural calculations. And we had to assume certain material properties. So this is what we assumed. These are well below what we got from the lab testing, okay? And then we plug this into a fiber section analysis, and a fiber section analysis assumes that plane sections remain plane after bending. You slice the section up into slices, and then because you know the distribution of strains, for example, fiber I on the left there, if you go all the way to the right, you can get its strain for a particular level of curvature, and that means that you can go into the figures that I showed in the previous slide, get a stress. If you know the stress, you know the force. If you know the forces, you can check for equilibrium in the section and then iterate until you reach equilibrium. But once you reach axial equilibrium, then you can calculate the moment capacity by getting the moment, the differential moment due to every differential slice. So if I went too fast, that's okay. That doesn't matter too much. What matters is that we could then plot what we call a moment curvature relationship. As the curvature increases, the moment in the cross section increases. And what I'm showing here is one that was used for design. This was for a 2-foot wide strip of the panel that I will show very shortly. The moment capacity was almost 2,400 kip inches for this particular cross section. And you can see some interesting things in the moment curvature relationship. For example, you can see first cracking all the way down here. And you can see the steel yield where it yielded, and eventually crack localization. So that means that under service conditions, the material is going to be operating in the strain hardening region, meaning the very dense, very fine cracking. Okay. Because again, also we were concerned about this. We hadn't done this before. We were a little worried about it, and so we also compared to the FHWA method, even though it hadn't been approved, which is also based on compatibility. And so again, we used, this is a hand method, which is very similar in a way to the moment curvature relationship I got before, but in a simplified way. You got the tension in the steel, the tension in the UHPC, the compression in the compression zone. You check for equilibrium and then get the moment capacity. So I won't elaborate because these are basic calculations, but I'm happy to answer questions about this later on if you'd like me to. Now, there were questions in the set of questions we got earlier on about shear and punching capacity, and I had those in before. But look at the equation for shear. This is from the FHWA guidelines. You will recognize the B times D, right? That's the cross-sectional area. You might recognize the cotan theta from first principles, although this is based on the modified compression field theory. But what is odd and weird is that it's based on FT localization. That is the tensile strength of the material at the localization strain with another factor attached to it. So basically, you are relying on the capacity of the fibers to give you the shear capacity that you need. And in this particular case, we had a strength that was much more than was required for the demand, and no stirrups were required. Although the designer insisted, let's add a few in just to make sure that the bars could be placed and things like that. But we did not require stirrups for the cross section. Punching was another one of our concerns that came up, but we couldn't find guidance for that. So we used a conservative model, again from first principles. We assumed the tire footprint, we assumed the punching area around it, and using just a very conservative model, assuming that the tensile capacity was a certain value, we showed that we had 10 times the capacity for punching in the very thin panels that I'm going to show you that went up for this particular bridge. Okay, so here is it. So this is the design. If you look up on the figure on the right to the top, you can see that there are 6 panels side by side. In between them are closure pores. And if you look at the bottom left, sorry, I meant left for the top left. At the bottom left is a side view. You can see the panels. What is interesting is that the guardrails do not continue over the girders themselves or the panels themselves. That was a thing that we did not want to worry about because the panel components were so thin that we didn't want to overload them in any way. And so basically we used a long span guardrail that has been pre-approved by MDOT for TL2. On the right there, you can see the joint, the closure pore. The closure pore is quite small compared to traditional closure pores. And the reason is because the bond capability between the bar and the UHPC is so high. In our testing, we showed that for these bar sizes, you could get away with 2 to 3 bar diameters in terms of the transfer length. But in this case, of course, we used a much higher number. And this is a cross-sectional view. You can see the truck. This is to scale. And you can see the panels side by side, and the truck is so much bigger. That's an 80,000 pound truck sitting on these very thin panels. And the panel is on the top right there. I'll show you the dimensions in a moment, but I just wanted you to gauge the geometry. Those of you who are bridge designers will kind of get a feeling for this, of how this looks compared to their previous designs. So we have the thin panel on top, which was 3 inches deep, and the stems were 10 inches, 10 and a half inches. So the total depth was 13 and a half inches for the 24-foot span. This is the cross-section design, showing again, you can see the 3-inch typical depth of the panels in the middle. And again, for experienced designers, this may be a little odd, such heavy reinforcement at the bottom for such a thin deck. And that is true, but it's not a concern because the UHPC is so strong in compression. For service conditions, the compressive stress was about 7 to 8 KSI, and that is nothing for the UHPC that was used. Okay. The reinforcement on the bottom, by the way, those are 4 number 8 bars. Now, after the casting was done, we were taking samples, and Bill and his team were doing that. And these were sent out again to another third party for testing. And in this particular case, this is the curing time in days. And on the bottom were the strengths we achieved. If you look to the very left, after 3 days, you get about 15 KSI. So it strengthens very quickly. and then it kind of slows down. So after a week, you get about 20 KSI, and it kind of remains steady for a while. And by 28 days, it had reached about 24 KSI. So that is more than what we assumed. It's a little bit less than what we had achieved in the lab, and that is understandable. Now, we weren't really concerned about compression. We were concerned about tension. Will the material that is truck mixed in the field, something that we had not done before, would it achieve strain hardening behavior? That was a big unknown for us. And so we asked Bill to take these types of samples for us. These are tensile coupons. And these tensile coupons are then put in a machine and then they're pulled apart. But because Bill's team had not done these before, we do these on a daily basis. And so many of them actually just failed incorrectly. They failed at the head, or they got crushed at the head. But there were enough of them, there were 7 that survived, and from which we got the tensile information. And basically what I'm showing here are the tensile results. For me, I was pretty impressed to see this. In fact, the localization strain was higher than what we achieved in the lab, and I'm not sure how to explain that. The tensile strength was lower. Remember, it was 1.82 KSI in the lab. Here it was closer to 1.5, 1.4 something. The localization strain was about 5 to 10% more. But the other thing that I see is that there's more variability. And okay, I'd accept that, I think, because of the way the specimens were made and because it's a field, these are field specimens. Okay. So I'm gonna, well, Bill, I'm gonna turn this over to you because this is the construction process and lessons learned, and then I'm gonna take over towards the end. So all yours, Bill.
Great, thanks, Sherif. All right, so we'll get into construction a little bit. That's the fun stuff, right? So Sherif dazzles you with all these numbers and figures and that, which are awesome. So I'll get into the project itself. So here we are. This is on site. We used some GeoWeb under the foundation, which was the Ready Rock walls. So we prescribe to, try and use ABC construction whenever we can. So using geocells with the stone there, it made a good use for the Ready Rock abutments. So going on, here we are with the Ready Rock blocks. This is our first time using Ready Rock blocks. They weren't perfect, but they were pretty good. There was some where the nubs didn't line up exactly correctly, but given the low dead load of the bridge, a lightweight foundation could be used here, like this Ready Rock walls. We were discussing during design, should we design for a traditional concrete deck, steel I-beam, or should we design for the lightweight panels we're producing? And it was agreed upon that we would design for what we're putting in there and not assume a failure in 10, 20 years, assume that the UHPC, which we have confidence in, would last a long time. So here it is, here's the form. So initially this project cost probably a little bit more because the UHPC has this particular design, and the precast plant was a little concerned at first, and then so basically they didn't know if they'd ever do this ever again. So basically the cost of the panel, which they used, was absorbed by the project. So we are doing some more casting at that plant, and the cost to cast these things has calmed down substantially because now he has the form and he can use this over and over again. So like Sherif talked about, we used a ready mix truck there at the plant. We bought the materials in super sacks mostly. Our guys had no problem mixing it. This was the first time we've actually mixed it in a ready mix truck. We've done small batches in like paddle mixers, but this was the first time using this one. And a day or two in, it was like clockwork. It was normal. So here we are again, adding the water and the high range water reducer. We do have a problem. There's times where we want to add ice, and on this project here, we cast it in July and it was getting warmer, so we replaced a lot of the water with ice. This material will heat up fast and it will start curing quickly. So like Sherif's design calls for pounds of water, we replace a lot of pounds of water with ice. So it helps us work it and get it in a little faster. So the steel fibers, this is one of the things that takes a little bit longer to do. So once we know we have the right slump, and we look at the truck, and most trucks have a flow meter on it and a pressure meter. So we'll watch that truck and then the flow meter. Once it's the right fluidity, we then start adding the fibers in there. So as you can see in the truck, maybe you can see a little bit, there's a small blue, almost like barrel on top of the chute. That's got a little vibrator to it. So what happens is these steel fibers want to lock together. So if you dump the bags in, we have this vibrator on that shakes that little screen. It helps the steel fibers kind of separate and go out throughout the truck. So here we are at the plant. So we mixed all materials outside and then just pulled right in the door and we cast the panels. So it is running out just like normal. And after day one, we learned a lot. This first panel we cast, the guy said spent 3 hours pulling the actual panel out of the form. So day two, we tried to pull it out. They spent 3 hours and they said we can't do it. So they did some slight modifications to the panel after the first day. And every day after that, the panel came out of the form rather quickly. So here it is with the fully cast finished panel. It only takes about, I think it was about 25, 30 minutes. The mix was in there. It's self-consolidating, so you're not vibrating it. Because if you vibrate this material, you change the striations, the orientation of the steel fiber. So basically, it'll smooth, it'll flow. The top surface has got a little skin to it. And it's not perfect, but we've learned to work with that in the end. So just for curing purposes, we just wrapped it in wet burlap and then visqueen. Wrapped it for a day. Next morning, about 7 o'clock, they came to the plant and they unhooked it all, and then she was curing away. So as you saw, we actually cast our coupons in that and left them in the same curing environment, so we could kind of mimic what was going on. That's why we cure them there at the plant and then took them to the lab to be broken. So on site, you can see that little turquoise mixer. That's our paddle mixer. We have mixed this plenty of times on site, so this was easy for us. The joints are super small, which we love. This stuff doesn't want to run, and so if you have large joints, just FYI, this stuff will push through your joints and through your forms, and it'll run, and it'll go out where you don't want it to go. So really, the forming for this thing has to be watertight because it will run, and you'll have a mess in your hands. So as you can see, here's the 3-stem bridge unit. It's almost like double T beams. I'm sure a lot of people across the nation have those. This is a triple T, and it is slim, it's durable, and the weight savings is incredible, which helped us with the foundation and the footing for it. So again, here is the finished design. You see the guardrail clear spans the bridge, which is one of the factors we talked about. Just getting the amount of reinforcement in the bridge deck to make the guardrail work. Something we don't want to explore at this time. So we'll probably look at that in the future with these precast panels. So here we are with the savings. So again, Mike Clark is our bridge engineer, myself, and we looked at, we don't just always go to UHPC in these structures. So we use wood, we use aluminum boxes, we use steel boxes, we use arch pipes. We go after everything. So we don't have a one-size-fits-all solution. So every solution is a little different. So so basically, we came up with the MDOT scoping spreadsheet based on this length, the bridge deck size, and that. They estimated the bridge would cost about $560,000. So we didn't go through and design the whole bridge and estimate it at $560,000. We used their standard scoping spreadsheet, which adjusts every year. And so that's where we got the numbers from. So our cost was about $380,000, all said and done. So like I said, we did all the excavation. We poured the concrete. We actually got the panels from a precast facility in Lansing, about 2 hours away. So we were there every day for about 8 days pouring these things. So in the end, you can see that we saved about 32%. And in the end, the long-term savings is what we're trying to capture, because we're here tomorrow, but who do you know is going to be taking care of your bridges in 10 years, 15 years? We don't know that. So we're trying to create a structure that will last 100 years with minimal maintenance, because we had some, in our agency itself, we've had some years of bad maintenance, unfortunately, and that you have a couple bad years of maintenance, and then you have some failures, and then you're on borrowed time with your bridges. So a lot of things I've learned with this thing, and we're getting better with this material every time. So.
All right, Bill, I'm going to take over. I have a few more slides about what has happened since this bridge and with the lessons that we learned from it and from Bill's team and from other Michigan projects as well. So at the same time as that bridge was going up, this bridge was also going up too. This is the first bridge in the US in which the UHPC deck is composite with steel tub girders. And again, 6 panels side by side with closure pores between them. The deck itself, again, is 3 inches at its thinnest point with the stems that were 3 inches. So you can see here on the left, you can see the shear studs on the tub girder on the right. You can see also the shear studs also on the tub girder with the corrugated sheets, the deck sheets in place. They were formed in a specific way in order for us to capture the ribs that we wanted. Again, a very lightweight deck on the steel tub itself. And because it's so strong, the steel tubs themselves were much smaller and they did not have to be cambered. So there were cost savings on many levels. Again, the process was done through truck mixing. There's a lot of experience by then. You can see on the left the sand going in, on the right the steel fibers going in, the girders being placed side by side. You can clearly see the closure pores, the construction site from above. Okay, this was a bigger stream now than the other one, and a longer span too. This was about 35 feet long. And from the bridge designer, Guy Nelson at Valmont, he was saying that the lightweight of these units was very helpful for the design itself. He estimates that the precast bridge units required only a third of the concrete in a conventional bridge superstructure and less than a quarter of the weight of a concrete PBU. Basically, again, terrific savings in terms of the weight, which translates into big savings in the overall structure itself. He estimates a 100-year maintenance life for the tub girders, which are galvanized. And of course, the deck itself is also going to be very long living because of the high durability of the UHPC. So this is the finalized structure. This is the actual data. The MDOT scoping worksheet was $790,000. The Clair County bridge cost, and this is Dwayne was the person who was doing this, and Dwayne is one of the panelists. His cost was $534,000. The short-term savings were about 32%. It's just a coincidence that it's very similar to the other one. And based on what he said, he could have definitely saved more, but that's the learning curve. And I'm going to show you another bridge in a little while where the savings was more, which is this bridge. So again, Dwayne is one of our resident experts now in UHPC. This is the Athey Road Bridge. This is done using the same type of system. For the Bricker Road Bridge, you can see it's a small stream in this case. Cross-sectional view, again, the three stemmed panels. On the bottom there, the heavy bottom reinforcement and the very thin deck made of UHPC, the very small closure pores. And again, the concrete coming in from a truck. And again, substantial short-term savings. And Dwayne made good on his promise that, okay, the MDOT scoping worksheet was $550. His cost was $248, 55% versus the 32 before. But again, really, this is not only about the short-term savings, but the long-term savings, which I would like to discuss in a minute. One more bridge, the Gratiot Road Bridge over the Moog Drain. Same type of cross-section being used. As you can see, very similar to what we had before. Wait a minute, this is getting boring. They all look the same, right? Except right now, this is the newest bridge. This is going to get cast this summer. And this summer is over, meaning the end of actually August, that we're going to use a quarter less fiber usage in order to save on costs. So going back to the NCTRP data, we had that the type X, the test data showed that the type X was more advantageous in terms of the localization strain compared to the smooth fibers. So even though you could have used generic fibers for the Bricker Road Bridge, in this case, we decided to go a little bit less in order to show that we could save on these and therefore make these even more economical. And because of that, the bridge was redesigned with the smaller localization strain, and basically it is going up right now. Now, in my final few slides, I want to mention a couple of things. So if you put a cubic yard of concrete, which is what, $200 now maybe, basically that does not exist in isolation. That exists with many other costs. That's our cost as an engineering community, the construction community costs, transportation, all of these things. And those numbers range from 3x to 7x based on a paper that I had written with Dwayne and others a couple of years ago in Concrete International. Let's replace this with UHPC. Well, the material is more expensive, but you're using a lot less. If you remember, Bill's bridge had 2/3 less material. So even if the material is 7 times as expensive, which it is about that number, then yes, the overall cost of a cubic yard is more. But because it's so light, you do not need pile foundation. You might need the foundations that he showed. Transportation is cheaper. You don't need a crane. In his case, he did not hire a crane. He did not rent a crane. He basically used the backhoe to lift the panels. So all of these are savings that go into the other costs. And of course, the real opportunity for cost savings is the long term. So, you know, we put in our regular concrete structure. After a little while, it needs some maintenance, and then you get sick of the whole thing and replace it. Okay, so I'm being generous here that over 100 years, you replace it only once. We think that UHPC, with the test data that we have, will not need a replacement in 100 years, maybe even more than that. Okay. So Michigan has been a pioneer in UHPC technology. A lot of this can be traced back to MDOT research that was done in 2012 and 2016. So it's host to many firsts. The Bricker Road Bridge, which I just showed. In fact, the very first bridge to use an open recipe UHPC was in St. Clair County in 2018. And going down the list all the way down, the first bridge to use 1.5% by volume steel fiber dosage, that's coming up in 2023. So some final thoughts about the cost considerations. So the cost of open recipe UHPC, and I know many of you will be interested in that. Those are numbers from Duane in Clair County is $13.77, from Bill is $16.75 per yard in 2023. These are actual numbers. These numbers have risen dramatically because of inflation. In 2019, when we did the bridges then, the cost was $890. This includes the fiber, which is Buy America compliant, and all the components of the material itself. But UHPC provides cost savings, not because the material is more expensive, but because if you change your thinking and take it into account from the beginning, you have these new opportunities. So you do have opportunities for short-term savings in spite of the high material cost. And basically, you have cheaper transportation, cheaper handling, no camber in many cases, smaller cranes, smaller substructure. And the long-term savings are also extreme because of the durability. So minimal maintenance, extremely durable decks, significantly lower replacement costs. So overall, we think that UHPC for certain applications is a no-brainer, and I think we should explore this more for building our infrastructure. I think UHPC presents a compelling case, and we've shown in the bridges that I just described, and I believe this is close to my last slide, the 32% savings. It is unique material that enables outside-the-box thinking. Certainly there are problems, as is with any new technology, but these problems are surmountable. You should not be afraid to use it. I believe it's a game changer that will transform our transportation infrastructure into an ultra-durable and ultra-resilient one. So I would like to acknowledge these individuals and the funding agencies that funded this work. And I would like to leave you with our contact information. I'm sure, and speaking on Bill's behalf here, that we would be happy to answer any questions you might have. And over to you, Mary Lou.
All right, thank you, Sherif, and thank you, Bill. So at this point, we will turn it to Paul Lyles to moderate the question and answer period. Paul, it's all yours.
Well, thanks, Adirad. Actually, Paul's going to take the second part of it, so I'll take the pre-webinar questions here first. We got a variety of them for Sherif and Bill. Some of them that came that you have addressed already, and I got a few of them that I'm going to let me look at here. So when you're talking about the life cycle, there was reference somewhere along the line of 150 years, and I guess how do you estimate or assess the extended life cycle on using the UHPC?
Okay, that is a good question. That is an estimate. Obviously, none of us are going to be here 150 years from now to check out this claim, but based on the test results we have seen in terms of freeze thaw and in terms of rapid chloride penetration, we estimate just a linear relationship based on how long concrete decks, for example, last. We just do a ratio. So I think that 150 years is actually a pretty conservative estimate. In the third international symposium that happened just a couple of months ago for UHPC, the estimate was maybe up to 1,000 years. I don't know, but that's where the estimate comes from.
So we definitely won't be around that long, but so.
For sure.
Can either of you comment on the type of rebar you used? I noticed even in the chat there was something about black bar versus epoxy bar, and maybe the grade of rebar that you end up using.
Bill,
well, I can answer that. We did specify it as black bar, but the precast plant said I can get epoxy coated just as fast and actually the same price. So we went with epoxy coated, even though it wasn't required. But they chose to go that route because they had it on site and they're real familiar with it. So. Okay,
good. Is there any movement towards regular production of UHPC pre-stressed eye girders? I guess I know Sherif wanted to expand into the pre-stress area, I guess. Is there a, where's that?
I would defer to our panel because we have two other people on the panel. So Ben Graybill from FHW, he's very knowledgeable. I would say he's one of the most knowledgeable people in the country about this. So I would defer to his response.
Sure. So there is some movement towards that. There's precasters across the country who are developing their own mixes or hiring consultants to develop their own mixes for UHPC, and they're starting to look at that market and see whether there's a place for them. So yeah, there is some movement, and I think over the next few years it will come to pass.
I concur.
So I guess to add on to that, currently, is there other UHPC superstructures being designed at this time?
Yes, so I mentioned the one that is going up in at the end of this month, and I believe that Dwayne, I'd like him to answer this question. He is, again, one of the leaders in this in Michigan in terms of the number of bridges he's done. So Dwayne, all yours.
Yeah, so you guys showed the one on 8th Road that we just finished about a month ago, and we've got one we're setting the same panels that Bill did. We're setting those next week, so that'll be my second one for the year. And then this fall we've got two more planned that are we're using the old abutments and a little bit different design, but it's a full UHPC deck panel again. So hopefully by the end of the year, Clair County could possibly have 5 total bridges. So that's where we're working towards.
Good. Kind of back on that life cycle thing. So UHPC is said to be difficult to repair over time because it doesn't, somebody states it doesn't bond well to itself. I guess how would repairs be handled in the future if there's needed?
And do you want to take this because it's part of EDC 6, right?
Ooh, it's not actually part of EDC 6, but I can offer some thoughts. You can repair UHPC if you need to. It's really about prep. UHPCs can have very smooth surfaces, so you need to roughen that surface. You can use traditional concrete roughening techniques in order to, like hydro demo or sandblasting, or cutting tools work. You need to prep the surface so there's something good to bond to. As with any time you're putting some sort of second thing on top of a substrate thing, you got to make them stick together.
Okay. There were a lot of pre-webinar questions about cost, and you guys addressed cost quite a bit and went over. Is there anything you'd like to add? There was everything from what's the comparison square foot wise to cubic, and I think you covered quite a bit of that, but I didn't know if there was anything you'd want to add in the cost comparison area.
I would like to, maybe my colleagues on the panel and Bill might have something to add, but I'd like to say that the cost of the UHPC itself doesn't really matter that much because the savings on other fronts are so substantial that I don't think that the price of the UHPC matters. And saying that, I would say that there are many excellent proprietary products that are out there, and any of them I think would still have led to cost savings on the projects we showed. The main thing is that you should not use UHPC as a replacement for concrete. You should design the project from the beginning to take advantage of the UHPC capabilities. Then you will see the cost benefits.
Okay, good. Let's see, something in general here. Interested in carbon negative cement product, uses salt water instead of fresh water with high compression and tensile strength. Do you see any avenue of using salt water in place of fresh water? Is there any advantage or any advantage, I guess you'd say?
Ben has been mixing UHPC more than me, so Ben, have you ever used salt water?
I guess I'm not quite sure where that one's going. Mixing salt into concrete where we've got steel in there and UHPCs have steel fibers in them, that's often not a good idea. So I guess I'm not sure exactly where the question's coming from, but it doesn't resonate with me.
It may be that, in an area where fresh water is not as available, maybe salt water, would be something that could be used in place of it, possibly. Maybe that's where that question comes from. So it's a possibility, but not something we highly recommending at this time, right? So, all I guess with that is Paul. Did you have you ready to talk about some of the questions that came in the chat?
Sure thing, Rick. I can take some. We got a whole bunch of them that have come in. And let me see if I can find some of them here. First of all, let's say, what is the effect of winter salt on this type of bridge surface?
Well, I think this project is basically waterproof. And then to finish this project off, we had the panels and we had the joints, and we actually finished it off with a epoxy overlay. That's good, I think, for about 20 years. So it's just a wearing surface, but I don't think it was necessary. We're trying to work out the details with Sherif on how to avoid that part of it. But this road being gravel, I'll be honest with you, we don't salt gravel roads, so it won't see much salt in its life.
Okay. How is the deck effective in flexural tension if rebars are placed at the midplane of the deck?
So the question is, how are deck rebars? The deck rebars are really, in my view, they're not needed, but typically you would place them for construction purposes. But really, there's no. I think the decks are, because of the location of the stems, they're so close to one another. The bending capacity is not something I would be concerned about.
Okay, you did mention punching shear a little bit.
Yeah, but those bars don't play a role.
Okay.
In the punching shear.
Okay. Did you have any concern for the lifespan of the dry cast module block walls that are under the bridge?
I don't have any issues with that. They're high strength, precast. They've been using them for many years for retaining walls and abutments. So we're not concerned whatsoever.
Okay. Can your the concrete, when you mix it, can it be placed with a pump truck?
We have never experimented with that. I'm curious what Bill thinks, but I would say that there are other proprietary products where they've shown that. But I believe it could be pumped, but we have not done that because it's quite fluid. So if you pour it on the ground, it kind of spreads in a something like a long distance. So Bill, do you have insight into this?
Well, I'll be honest with you, to get a ready mix truck to do this work was tough to begin with. In Michigan, this isn't used a lot, so we found someone that had old trucks laying around and we could use their truck. We asked the plant if they would mix this material at the precast plant in their silos, and they said not going to happen. They don't know it well enough to trust it. They don't want to gum up their plant next. They have they can't use their mixer anymore. So to leap of faith into a pump truck, man, I don't know. That'd be a tough leap of faith. I mean, you ruined a couple hoses, and what are we buying? I don't know if I'd go that route yet.
Okay. Let's see. Will future UHPC projects from St. Clair County be led in an open tender bid?
Good question.
Well, we did one project already. It was actually Everyday Counts project. A contractor actually did precast units, and actually all the joint connections were UHPC. So we have done projects with contractor mixed UHPC. So it all depends on the size of the project and the scope, and if our crew can handle it.
Okay. Will steel fiber be a problem after wearing and exposing, or grinding, or grooving the deck?
I don't think there's an issue with that, do we, Sherif?
Yeah, I don't believe so. Basically, what will happen is that any fibers that stick out will eventually rust and fall out. When we were at the Third International Symposium, we went to an overlay, a couple of them actually, where the decks have been out there for several years now. And basically, the fibers are rusted, they've fallen out. Some of them actually still exist after 6 or 7 years now. And once that happens, no water is going to get inside. The fibers are protected by the extreme impermeability of the material. So I don't think so.
Okay. Does UHPC exhibit better performance in terms of durability as opposed to an ordinary concrete with a very low EC ratio?
Yes, and the reason is because of the packing theory that is used to design it, and that is where the components are designed to fit together very nicely. And so because of that, I think that it would perform better than any other type of concrete. But obviously I haven't tested the others, so I can't say definitively. But from what we've seen, it is extremely durable. I know that others on the panel may have, tested them for a while or used it for a while. I don't know, Ben, how long you've tested others or.
We have, yeah. The UHPC is very impermeable, and most degradation mechanisms for concrete that we deal with in the infrastructure world deal with permeability. So liquids getting in with salts that cause degradation, or liquids getting in and causing freeze-thaw and that kind of stuff. So if the waters can't get in, then the concrete's going to perform better. So that's the main reason why UHPC just works so well.
Okay.
Paul, I'd like to go back to the pumping question a few questions ago, because I've been thinking about that. I mean, the concern about pumping is that the fibers might damage the hoses, but you have to realize that these fibers are half an inch. They're kind of like this. And I really think that as the viscous thick liquid that is UHPC, fresh UHPC, goes through, this will just slide by the surface. It would not cause damage to the hoses. That's something that people need to experiment with. Just as we managed to convince our local precasters to do this, I think that someone should try it out. I suspect it's going to work. So I just wanted to bring that out.
Okay. Here's an interesting one. Because of the close packing and everything, can longitudinal reinforcement be placed closer together than AASHTO bridge specs allow for clear distance between bars?
Anybody else on the panel?
I'll say what the new AASHTO guidance suggests, and that is you still need to have room between the walls and the rebar, or two pieces of rebar, so that the material can flow between it. And that flow is generally controlled by the size or the length of the fibers. So if your fibers are 1/2 inch long or 3/4 inch long, you need enough space that can get through. So it could be closer than sometimes is required for AASHTO, but there are limits. You have to let it flow.
Yes, I concur with that, and I would say also, extending the question would be, can you place the bars closer to the edge than what AASHTO requires too? I mean, if you wanted to extend the question, I would say yes as well. As long as you don't have localization, your bars will be protected much better than in regular concrete.
Okay. On slide 59, we had a few questions here. Is this the same bridge? I thought it might be a different one.
This is a different one. This is the tub girder bridge.
The question was, did you increase your slab thickness to get the guardrail on the slab?
I am not as familiar with this as Dwayne might be. Dwayne, do you have a?
We did, yeah. There was a design criteria for attaching the guardrail posts through the. We precast it with bolt holes in the UHPC, and then there's a bottom plate, and then a kind of a standard guardrail post with a base plate on it, and then it's bolted through the deck. But we did thicken the deck up. I think it's 6 inches on the fascia to meet the crash design.
Okay. We do have a whole lot of questions that are still coming in, and Torrid has given me permission to go till 20 after. The people that are hanging on and want to listen, and I'll see if I can get some more of these. Was there any comment about vibration when the section is so thin?
I don't have Sherif giving on that one.
Yeah, you don't need vibration. The material is self-consolidating. You do not need vibration.
They're talking about vibration of the bridge, I think.
Oh, vibration.
Service.
Yes, this bridge met all AASHTO requirements for deflection and all of that. The high modulus plus the section being almost uncracked helps with that.
Okay.
So no.
And we had some questions on the once again on the guardrail. And I don't know if you're familiar with TL4.
I am.
And how thick would the slab be? How would you use a thin slab in conjunction with the very heavy crash test?
I will go ahead and answer that. So we've been doing a lot of research all the way up to TL6, but mostly not for not for UHPC. So we haven't, so I don't have a good answer because we haven't investigated UHPC. You have the issue, of course, of the bending and the tension coming from the impact. I think you will have to have a specific check to do that. You might have to have cross beams that might be designed for the very high forces that will come from a TL4 guardrail.
Okay. Question here about your tub girder you had. How do you inspect inside the tub?
Dwayne?
There's actually a porthole designed in the tub girders for interior inspection.
Okay. Then we had a part of a question that came up, and the people asked about what did you do for camber on your bridge? It's 30 feet long. It's not real big, but did you have any issue with camber or anything like that?
No, the design didn't require camber at all.
Okay, so
It is so light that it doesn't become an issue. Regarding camber for this bridge, the one that's on the screen, that's 36 feet long span. If I'm not wrong, Dwayne, you did not camber this as well, right?
That's correct. There was no need for that in the design that Guy did.
Oh, okay. They are pretty light. I don't know, and you got a pretty good modulus, so compared to normal bridges, that's interesting. Let's see. And then, how light is the bridge compared to normal concrete?
Two-thirds lighter.
The difference would be 2/3 lighter. Wow. What type of bearings did you use on the bridge?
We use elastomeric bearing pads.
Okay, just a strip pad. All right, we just one under each little stem.
Yep, exactly.
Okay. All right. Then, because the bridge is so light, were there any hold-down anchors that you would use? And they were concerned about possible wind loads or even in a flood.
Oh, there were anchors into the abutments. Yep, each stem had a little anchor in it. Yes.
So they were anchored down. Okay.
Yeah.
Okay. Let me see. You want to elaborate any on that the concrete roughening to get the bond to between the different material, if you're repairing it or when you're pouring your closure pour?
Sure, I think that goes back to me. You definitely need to create a bondable surface. So it's got to be clean and it's got to be rough. It's got to have some micro texture, so it can't be like just undulations but smooth. A lot of the work recently on this topic has come from connections where you're using UHPC to connect to either UHPC or conventional concrete, and also for overlays. So using UHPC on an overlay of a deteriorated existing bridge deck. So how do you make the things stick together? So hydro milling or hydro demolition, very high pressure water, has been shown to work very well. I know it's not the most commonly available construction service, but it does work really well. People have looked at other methods and they can work, but you have to make sure you don't create too much distress in the substrate. So if you leave behind concrete that might be clean and rough, but also full of cracks, you're going to be hurting yourself in the long run.
Okay. There was a question that came in if you used a link slab here. I don't think you did. It's just a one-span bridge. You didn't do anything like that. So that was one that came in. Then the total mixing cycle, someone added it up and said it came out to be 47 minutes. Is that correct, or is there any way to improve on that, or what do you want to comment on the mixing cycle time?
Well, I can a little bit. So with this product, so we had we didn't buy the cement or the slag separately. There was a plant nearby, a ready-mix plant. They actually drove it. So we put the sand in first at the plant, because let's say there's a little bit of water in the drum still. On our project, we put the sand in the drum, dried out a little bit, and drove to the plant to get the cement and the slag and put it back in and dry back. So we probably could bring that down a little more, but we, instead of buying the bags of cement, super sacks, we went to the ready-mix plant and got it there.
Okay.
I would add that in the lab, typically it would be less than this. If you had all the products ready and ready to go, it's less than 47 minutes. I think anywhere from 30 to 45 minutes is kind of the range that you would get with a truck, but not less than 30 minutes. So that is one of the limitations of UHPC. It does take longer to mix.
Okay. It's 21 after, and I think that's all the time we have. We still have some more questions out there. So we will answer those and get them posted to the on the webpage. So I'm going to turn it back over to Antoine. And Antoine?
All right, thank you, Paul. And very interesting, certainly, webinars. And thanks to our presenters and the people who participated in the question and answer period. Certainly, very impressive group of people that were involved in this presentation. So, the question, as Paul said, is just keep coming, which shows the level of the interest on our audiences on the topics. So, and one last word again, those of you, as I mentioned early on, that interested to be a member of the ad hoc committee for the development of the next generation of the transportation asset management system that is going to be beyond just the bridge asset management, please send me an email. On that note, we are going to conclude our monthly webinar today. Again, thank you to all the speakers and hope to have all our audience with us for our next webinar. Thank you.